My name is Fuzzing from Tsinghua University, and I'm happy to give a talk on our recent work named LOKI, which is a state-aware fuzzing framework for the implementation of blockchain consensus protocols. And I'll start by introducing some background information about consensus protocols. And they are originally taught in the distributed systems. Considering that there are so many complex situations in a distributed environment, such as package disordering, node crashes, and network delay, a fundamental problem in distributed computing and multi-agent systems is to achieve the overall system reliability in the presence of a number of faulty processes. And in the blockchain systems, there are many consensus algorithms have been developed. And basically, we can divide them into two types. And the first type is based on the game theory, and the other one is based on the CAP theory. And the game theory-based algorithms leverage insensitive mechanisms to cause a big loss to the hackers who would like to make malicious voting. And typical protocol includes POW and POS in the well-known Ethereum, and some new algorithms like the DPoS, which is evolved from the POS protocol. And the other type of the consensus protocols are based on CAP theory. And considering that there are so many failures in the distributed system, algorithms that can tolerate crash fault or Byzantine fault are developed. So some well-known algorithms of this type contains the well-known RAPT or PBFT. And I will briefly introduce the typical consensus algorithm PBFT, which was developed a proposal first by the Dr. Lamport in 1999. And PBFT aims at achieving consensus even there are Byzantine nodes. The design of the protocol contains three phases. And in the first phase, which is called the pre-prepare phase, there is a chosen leader, and it will broadcast a prepare packet with new blocks. And other nodes will then execute the block and send signed packets with their signature. And the second phase is called the prepare phase. And during this phase, if a node receives more than 2/3 of the signed packets from other nodes, it will then send out the commit packets to make sure of that block. And in the commit phase, a node will record the blocks in the network, and if it has received more than 2/3 of the commit packets from the blockchain. And in this way, PBFT protocol can always achieve consensus if there are less than 1/3 Byzantine nodes in the network. But we all know that consensus protocols play a very important role in blockchain systems. But they are nearly all of them have been proved to be correct in theory, but there may be some flaws in their implementations. And here I show an example of consensus protocol vulnerabilities in Hyperledger Fabric, which was discovered in 2021. And this vulnerability has been assigned with a CVE identifier. And this bug is just due to a simple non-pointer checking, as I showed in this figure. But if it is leveraged by a compromised node, this vulnerability can lead to a node crash. And thus, the blockchain may not process any new transactions. But this bug cannot be triggered easily. In a normal situation, there is a leader node, which is the node 1 in this example in the figure. It will first process the received messages by the function named process message. And in this phase, the node decrypts and validates all the enveloped messages first and sends them to the function named channel header here for further processing. And in this situation, there is no bug. The bug will never occur. But this bug is triggered in a relatively rare situation where a new leader is elected. And for example, in this case, the node 2 is the new leader. And after the election, there may still be some living enveloped messages in node 1. And node 1 will forward these messages to node 2 for further processing by using the function called process message. And here the bug may exist because this path has no verification for the messages, and node 2 only handle these messages directly with the function ordered. And finally, the bug is triggered and invalid memory occurs. So from the example, we summarized the two main challenges to detect the consensus protocol bugs in blockchain systems. And for the first challenge, it is hard to model the consensus state in real time. The consensus state is essential for generating high quality inputs for the input and the test. For example, for the case I just illustrated in the last slide, a testing tool can only trigger that bug by knowing that there is a leader switching state and constructs envelope messages with knowing pointer to the previous leader. But states are hard to be captured for two reasons. For the first reason, states of consensus protocols are dynamic and complex, which means that consensus phase is always dynamically changing, and the consensus nodes may not be maybe in the different consensus round at the same time. In addition, sending packets without knowing the states is ineffective, and the target node cannot progress the consensus and trigger deeper logic. Thus, most of the generated testing packets are invalid. So there are some traditional protocol fuzzers, such as Peach, but they cannot handle this challenge well. For Peach, it uses a fixed state model without knowing the current state of the system. And thus most of the generated inputs are invalid. And for the other challenge, it is how to construct the multi-dimension inputs according to the state. Here we mean the multi-dimension means that three aspects. And the first is the type of the generated packet and the content and the target. And for the first two aspects, traditional fuzzers such as Peach can only send packets with fixed types and mutate the content randomly. And for the target, an effective fuzzer should dynamically adjust whether it sends current packets to the maybe the leader, or determine how many nodes that the mutated packets should be sent. For example, the fuzzer may only send the packets to 1/3 of the nodes, but rather than the other nodes. Well, Peach always sends packets to fixed targets, which are predefined in its data model. So we designed LOKI, and here's the overall design of our system. And the key insight is to masquerade LOKI as a normal node to fetch neighbor states and fuzz them. And as the left part of the figure shows, LOKI nodes participate in the blockchain together with normal nodes. And now I will describe the workflow of LOKI. For the first step, LOKI listens from the blockchain system to receive network traffic. And LOKI uses the crypto part of the underlying blockchain to decrypt the received messages and put them into the model construction and updating process. And for the second step, LOKI will analyze the type of the received message and constructs and updates a state model. And here we give the details of state model construction and updating. And at the very beginning, LOKI will not just start the fuzzing process. And in this duration, LOKI decrypts and analyzes the type of the received messages and then constructs the initial state model. And in this model, each edge has the same weight. If one node in the model has n transfer edges and the weight of each edge is just 1/n. And after a few duration, LOKI will then update the state model together with the fuzzing process. And if a new message is received, LOKI adds a new edge and checks the subsequent messages. And here is an example of the PPFT state model. And we can see that LOKI first mines some heartbeat packets and corresponding responses. And after that, LOKI hears some consensus packets, such as new view packets and prepare packets, and so on. And LOKI will add these packets into the model and assigns a new transfer edge to the corresponding nodes. So let's move to the next step. In the third step, LOKI uses a message guider to guide and update the sending message type and target choosing. And in the next step, LOKI selects seeds from the message pool and feeds them to the mutator to modify the concurrent content of the messages. After that, LOKI mutates the message according to their type. And here we designs different mutation strategies according to the field type. For the numeric type, we just randomly mutate them to another number. Especially, LOKI will mutate them to some border values, such as the maximum of integer or 0. And as for the string type, we just use a similar strategy as the AFL or like fuzzer, which is the base or base flipping, to change it to another string. And for structure, LOKI mutates them recursively for each field. And for the cryptography field, LOKI just mutate them with the inherent cryptographic components from the underlying blockchain node's code. LOKI will mutate other fields first and then use the cryptographic algorithms to sign or encrypt these fields and fulfill the cryptography field. And in the step 6, LOKI encrypts and signs the messages and then sends them to the other normal nodes. And at last, LOKI use a bug analyzer to monitor the execution of blockchain. And here we have two types of bug analyzers. For the first one is a memory-related monitor, and it uses ASIN to instrument the normal node's code. And memory-related bugs always can lead to the node crash. And the other one is a monitor related to consensus logic. And LOKI check whether there is a bug that violates the liveness and safety feature of a blockchain system. And these bugs can lead to a consensus failure or invalid data store. So for now, we have implemented LOKI on 4 blockchain systems, including the Gold Ethereum and some consultant blockchains, including Hyperledger Fabric and Physical Because and DEM. And totally, we have detected 20 bugs in the systems with 9 CVE. And 14 of the bugs are memory-related bugs, and the other 6 are related to consensus logic. And here I'll give a case to illustrate the bug details found by LOKI. And this case is found in Physical Because, and it is a widely used commercial consulting blockchain developed by WeBank. And we tested a physical cluster with 10 nodes. And LOKI sent malicious packets to the other normal nodes in this cluster. And the malicious packets constructed by LOKI has a big value of the length field in the header. And thus, if the if condition at the listing at line 4 will be triggered, and the decode function will return 0. And the Physical Because node will think that the packets are not completed and allocate big memory for receiving the following content. Thus, if LOKI constantly sends the malicious packets, the memory will constantly be consumed, and finally the kernel will kill the node process and cause a node crash. For now, this bug has been fixed by the developers. And as for the coverage, we compare LOKI with state-of-the-art tools, including Peach, Fluffy, and Twins, while Peach only supports Gold Ethereum and Twins only supports DEM. And in conclusion, LOKI covers 30 to 180% more branches than other tools. And we also observe the coverage trend. We record the coverage every 20 minutes for 2 hours. And LOKI's coverage grows significantly in the first 40 to 100 minutes on the systems. And we also conducted an experiment to find out the effect of multiple LOKI nodes. And we set a group of 10 nodes for each blockchain with 1, 2, and 3 LOKI nodes and calculated the branch coverage. The result shows that the coverage finally converges at a similar value under various LOKI nodes. And more LOKI nodes may slightly accelerate the coverage increment. And our future work mainly focuses on the following aspects. First, we will explore more oracles, such as hard work or leader fairness, to further improve LOKI's bug analyzer. And in addition, we will try to cooperate LOKI nodes to share the message pool to further improve the effectiveness of LOKI. And at last, we will try to adapt the LOKI to more blockchain systems such as Quorum. And that's all. Thank you for your listening. Please contact me if you have any questions. Thank you.
What I actually wondered is for the state mapping, how do you map the different states to code and code to states? This seems like an arbitrary hard problem. And you say that you talked about your state inference and how much better it was than other systems. Like how do you map states?
Okay, the states here in LOKI system is just the we just infer the state by the received messages type, and if it's a let's say prepare packet, then we just know that we find a new state with a node just in the prepare constant state, and the state is not so complex in LOKI system. It's just marks the received messages type.
Okay, great. Thank you.
So
let's give him
I think
another.
principally we just mine that state model according to the received traffic. Yes.